Hey everyone, I hope you all are safe and doing good. So, in this lecture, let's see one more lead code question. And the question number 35 it's search insert position. So, you have to find out the problem statement is you are given a sorted array. Sorted array means you know, okay. And once you are going for these questions, lead code question, one thing I just want to tell you if you see a sorted array and you have to search something or find something, this kind of thing just think about like binary search you have to apply and you will get the optimal approach because obviously the thing is the main motto is you have to find out optimal approach. Okay, so we will see first the brute force approach, then we will go to the optimal approach. I'll show you the third process, how to think. If the problem is given, how to think about that problem, how to think of the solution. Don't just directly go for like a sorted array is given, you have to search, go for like binary search, that's it. Because in interview, if you first tell the brute force approach, then you tell, okay, this is the drawback of this approach in terms of time complexity, and then we have a better approach that is this, having this time complexity. So they will get to know that, okay, you have some idea about the things. Okay. You didn't just have cram these things like, okay, just go for binary search, that's it. Okay. So in that case, it will like leave a high impact on the interviewer. If you go something like this, first brute force approach, then optimal approach and all. So we'll see first here brute force approach, then we'll go for optimal approach. This is just one you can say shortcut or the I'm just giving you that if you think the array is sorted, if you see you have to search something, find something, the optimal approach would be use binary search. Okay, so you are given a sorted array of distinct integer. This thing is important. Distinct means no duplicacy of element is there, and a target value. Return the index if the target is found. If not, return the index where it would be if it were inserted in the order. So you have to basically find where you can insert and the condition is you must write an algorithm with log and runtime complexity. And if you are aware about binary search, then binary search algorithm time complexity is log n. Now example given is we have an array nums 1, 3, 5, 7 and the target is 5. Now see, check. If 5 is there, then return the index if the target is found. So just return the index. Index is 0, 1, 2, 3. So 2. Output is 2. Array is 1, 3, 5, 6. Target is 2. Target is not there. Target is found. Return the index. Otherwise, you have to find out where you can insert this target into this array. The array is 1, 3, 5, and 6. Now, where you can insert? The target given is 2. So, where you can insert this 2? Index is 0, 1, 2, 3. How you find out? And you have to return that index where you can insert this 2. Target given is 2 here. So if we with our naked eye if we see, we can directly tell that okay, it's a sorted array. So in like you can say ascending order. So it's 1. Now check it's 3. So you can insert this 2 somewhere here. After 1 before 3. Yes. But obviously there is no position or there is no index 0.5 kind of thing. Index 0, then 1, then 2, obviously. So where you can insert? Definitely after 2. So here we can insert this 2. So the search position or the insert position, sorry, is 1. In this case, it's 1. And the output is 1. In this case, 1356 target is 7. So 1356. Now target is not 2, it's 7. You have to insert 7. Where you can insert? If you see how to think now, just go for first brute force approach. Don't take stress of thinking the optimal approach. If you're a beginner, think first optimal approach. Sorry, brute force approach. How you can do this thing? Array is sorted, we know. Whatever we have, just think about that. Array is sorted. You are given a target value. What you have to find out? Where you can insert this. If the element is already there, return that index. If the element is not there, where you can insert that position, you have to find out. I think problem statement is clear to you. Now, the simple approach is we can go one by one. Generally, what we do is anyone will do what like compare this. Is this 1 less than 7? Yes. So definitely we can insert 7 after this 1 only. Go to the next element. 3 less than 7. Next element 5 less than 7. 6 less than 7. So after that only we can insert 7. Not before these because it's sorted array. end of the array. So if this is the case, end of the array, so definitely we can insert 7 here. So it will return the length of the array. Length of the array is 4. So 4. At fourth index we can insert. So it will return 4. I hope you got this. So we are going here linearly, one by one, traversing every element. So it's like linear search. You are searching for a position or that element using linear search, one by one. Starting from end, you are going linearly. You have to traverse, like this is the worst case, because element is not there and element is greater than all the elements. So definitely you have to compare with all the elements. At last, you just return whatever the array length. So you have to traverse every element. So it's like time complexity for this is order of n. N comparison you need. You compare the target with this, with this, with this, with this. If there are 4 elements. If there are, suppose we have array 1, 3, 5 and 6, 7, 8, 9 and the target in this case is 10. So you have to compare this target with this. So how many comparisons basically? 9 comparison. How many comparison? 4 comparison. That depends on the size of the array. Size of the array generally we take n. So that's why time complexity is in bigger notation. Worst case time complexity is order of n. You got it? Okay. Now, if you don't know about these things and this thing because we have discussed in my course Mastering Data Structure with Java, you can go and check out. There we have discussed like Java from scratch, everything, and then DSA will be discussing. So the link you will get in the description box of this video. If you are interested, you can go and check out. Okay. And there we have one live session as well in that course every week, doubt resolution session. So you can directly ask your doubts to me. That would be live session. And if you enroll in that course, you will get, you can say, access to a dedicated WhatsApp group. So there also you can ask your doubts. Okay. The link you will get in the description box of this video. You can go and check out. Now let's say this is linear search. Okay. Time complexity order of n, but you have to find out algorithm with log n. Okay. We'll think about this also. But for now, I guess the process is clear to you. How to find out the search position. Right. Now, let's write down this thing. So loop would be from here to here, we know. So let's run the loop. I is equal to 0. I is equal to whatever the array dot length. Suppose name is ARR and I plus plus. Because you have to traverse from this to this. We are comparing with every element. Now, if where you can insert. See, in this case, let's see. If I want to insert 2, what was the case if the target is 2? So is this element greater than this 2? No. Next check. 3 is greater than 2. As soon as we find out the first element which is greater than the target element, stop. And this would be your index. At 1 only I can insert 2. Suppose the target is 4. Suppose target is 4. What will happen in that case? Compare this element greater than 4? No. This element greater than 4? No. This element greater than 4? Yes. Stop. Here only you can insert at second. So position is second. Because array is sorted. Okay. Now, if the target is 5. So in this case, return the index if the target is found. Because we cannot insert one more 5. Arrays of distinct values, distinct integers. Means duplicate data is not allowed. So 5. Compare this. Is this 1 greater than? No. 3 greater than? 5 greater than? Okay, now 5 is not greater than 5. 6 greater than 5. So now how to return? So with that check greater than, you have to add one more check greater than equal to. Because if it's equal, then you have to return the index. So you have to check greater than and equal to. 1 greater than equal to 5? No. 3 greater than equal to 5? No. 5 greater than equal to 5? Yes. So return this index 2. Simple. So you have to find out what? As soon as you find out the first element which is greater than or equal to the target, that would be your answer. That would be your position. Which means you have to find out a smallest index. Because here, if the target is suppose 2, so this element is also greater than 2, this is also greater than 2, this is also greater than 2. But the smallest index, the first element which is greater than or equal to target. That's it. 3 is the smallest. So basically you are finding the smallest index, where you can say this array of this element is greater than equal to target. This thing you need to find out. So first go for that approach and then try to find out one condition or what you need to find out. Just write down that thing in this form. Right? Now linearly also we can find out how to write down that thing. Loop will run from here to here till the end of the array. If check the condition you have to find out. This condition you have to check. If this array of I greater than equal to target, if this condition is satisfied, return simply whatever the I is. As soon as this condition is satisfied, simply return that I. In that case, if the target is 4, compare this. Is this element, let's see, the target is in this case, I am having 4. So at first I is equal to 0. Array of length is 1, 2, 3, 4. So 0 less than 4, yes. Control will enter into this condition true. Array of I is 0. It's 1. 1 greater than equal to target, target is 4. No, condition is not true. Right? So we are not going to enter here, we are not going to return this I. Okay, and this is the end of the loop. But we are still in I plus plus. So I becomes now 1. Condition still true, enter here. Array of 1, this 3. Greater than equal to target? No. Will not enter here. I plus plus. I becomes 2. This 2. Greater than equal to target? Yes. Simply return I. Right now is 2. So 2 is the exact position obviously we want. We can insert this 4 here only after 3 and here. You have to just search the insert position, that's it. So here only you can insert this 4. Simply return this I. But in this case, suppose the target was 7. Target was 7. You cannot insert here. Condition not true, not true, not true, not true. But now, once you do I plus plus, after 3, once it becomes 4, condition is not true. So out of the for loop, what is there out of the for loop? What to return in this case? You can insert 7 at index 4. That is length of the array. So simply after this, return whatever the length of the array dot length. That's it. This is the logic. I guess that's not much tough. But it's linear, so it will take order of n times. How many comparisons would be there? How many times the statement would be executed? Because loop is running from 0 to length of the array. In worst case, we are basically write down bigger notation, the time complexity. Time complexity cannot be more than order of n in worst case. So the number of comparisons are depends on the length of the array. In best case, maybe you get the position here at first. Only one comparison you need, but that is best case. Best case for this is order of 1. Yes. Average case is also in this case order of n. Average case means, every case, for every case, just add the number of comparison, the time complexity divided by the number of cases. Okay, so that is average case. That would be also order of n in this case. Okay, now I guess this is clear to you. This is linear search. This is how? This is, you can say, brute force approach. But what can be better than this? Because array is sorted. We can apply here binary search. How? Let me show you that thing also. Then I'll show you practically this thing. Don't worry. Suppose this is my array. Suppose and target is 15 and you have to find out, like, obviously it will return because 15 exists. Suppose target I'm taking 16. So you have to find out the insert position where you can insert 16 here. But we will apply now binary search. I hope you are aware about binary search. Let me just tell you in brief. Binary search means you will not go from this to this if you search any element. We just divide this array by half. Suppose you want to search 15 is there in this array or not. Suppose I'm just explaining now binary search. So we have 2 pointer. This is low, this is high, or start or end, or I or j you can take. Okay, just divide these things, because low would be, I know, 0, and high, this pointer would be 7. Whatever the array length minus 1. If we have these two pointers, we can access easily these two values from this array, first and last. And we can find out mid as well. Mid would be 0 plus 7 divided by 2, that is 3.5. So integer, that is 3. So mid is somewhere here. I can access now this, and this element, 3 elements. Now target is 16. But in binary search, we compare now with the mid. Is this target less than 10 or greater than 10? The target is greater than 10. Yes. So it is sorted array. So can I surely say that the 16 I can find, or if target is, suppose I'm taking here 15, this 15 I will find in the right half. That is for sure. So why to search in this half? It's totally waste of time. Yes. So that's binary search. We keep dividing the array in half. So that's why the time complexity in this case is log n in worst case. 15 would be in the right half. So you have to search this only. So to go to the right half, we know high would be here, but low would be now here. How to point, how to move this low here? We can just do whatever the mid plus 1, that would be low. So 4 and 7. Now here I'm having my low, here I am having my high. So now this is the array, that's it. We have completely removed this part. Again, the same process you have to repeat now. So again, mid part. Again, find out mid. So that would be, I guess, 11 by 2, that is 5. This is the mid now. This is my mid. Again, compare. My target is 15. 15. Now less than mid. Less than 18. So can I say this 15 definitely exists in the left half? Yes. So you can eliminate this half. So to go to the left half of this 18 is now this only. To go to the left half, we just move the high. So now high becomes mid minus 1. High becomes 4. Low is also 4. 4 plus 4 divided by 2. Mid is also 4. Low is high. Low is here. High is also here. And mid is also here. Now the search space is only one element you have in this array. Now compare this 15, 15. Yes, you find the array and this return this index. That's it. If element is not there, suppose I want to find out here 14. Suppose target in this case is 14. 14 is, this is not 14. 14 is less than this. So it's 14 is less than, so it will exist in the left half. So to go to the left half, just to high is equal to mid minus 1. Now high becomes 3, low is 4, but now stop. Because low is here, high is here. So obviously there is no search space. You don't have to search anything. There is nothing to search. Once loop would be, condition would be low is less than equal to high, till then you have to repeat this process. But now here low becomes greater than high. Stop this, because now there is no search space, because we have already we've seen that this was 10 and we have compared with this. So we have moved this part. So if high is here, where is the search space? What to search now? Okay, stop here. This is basically binary search, and the time complexity is order of log n. So the same thing we will find out, we will use while searching the insert position, binary search, not linear search. Okay, let's see now. What to find out? The smallest index such that the element in this array is, you can say, greater than or equal to the target element. And if you are aware about something, lower bound, upper bound, then I guess this is the condition of lower bound. Once you find out lower bound of an element, then you have to find out smallest index where the element is greater than or equal to the target element. Simple. But if you're not aware about lower bound, it's okay, leave it. Now you have to find out this thing. Smallest index where the element of I is greater than equal to target. That's it. At that time, return that particular position. So in binary search, what we can do, we know now the binary search mechanism. So high in this case is 0 and low is 0 and high is 7. You have to find out mid. Mid would be 0 plus 7 divided by 2. It's 3. Right? Mid is here. Now this 10, is this condition satisfied? Is this 10 greater than equal to target? Target is 16. In this case, 10 greater than equal to target 16? No. Okay. So our target is what? You can say target is greater than the mid element. So we can find out our target in the right half. So move to the right half. To move to the right half, low becomes mid plus 1. That is 3 plus 1, 4, 7. 4 plus 7 divided by 2, it becomes now, sorry, 5. Now mid is here and low is here and high is here. So this is my array now. Again compare. Mid is here. Is this 18? Greater than equal to target? Target is 16. Yes, this is true. 18 is greater than equal to 16. Okay. So I cannot say that this is my insert position. I can insert where? Right now at mid is here. So I can insert here. Yeah, maybe in this case you are saying that you can insert 16 here. That's true. But maybe it's not sometimes. Maybe after 15 we are having here 17. Maybe. So I cannot say that here I can insert 16. No, because here we have 17. But yeah, this may be my position. This may be. I can insert maybe here. So we can have, like, at first suppose we are having position. Position is equal to length of the array. Hypothetical value length of the array. That is 8. Update this to whatever the mid is, 5. This may be my position, but I am not sure. I have to find out the smallest index where this condition met, where this condition is satisfied. Suppose let's change the array. Okay, not change the array because you have to change everything. Or let's change everything here. I am having 15, then I am having here 17, 18, 20, 25, something like this. It's 5, 6, 7, 8. So right now 0 to 8 we are having. So it would be 4. 0 to 8. So it becomes 4. 4 divided by 0 plus 8 divided by 2. Now here we are having mid at first. Right? And position at first I'm having 9 because total number of element right now is 9. So it becomes now 4. 15. At first we are having 15. So 15 greater than equal to target, greater than equal to 16. No, a target is greater than equal to 15. So target would be in the right half. So we have 5 and 8. Low would be this side and 5 plus 8 divided by 2. Now mid is here 6. Now check. At 6 we are having 18. 18 greater than equal to target 16. Yes, it's true. But we cannot say that, okay, this is my position. At 6th index, I can just insert 16. No, you cannot insert 16 here because we have 17 at the left hand side. If 17 is not there, you can say that. So this may be my answer. So we can have this. Yeah, this may be my answer. But you have to find out the smallest index. So we can just update it by 6. This may be my answer. Okay. But you have to find out the smallest index. So smallest index, where you can get the smallest index such that this condition satisfied, to the left hand side, because the index is 6. Smaller index than 6, where you will get? In the left hand side, not right hand side, definitely. So move to the now left hand side. So to move to the left hand side, just eliminate the right half. So you do high is equal to mid minus 1. High becomes now 5. This is 5. 5 plus 5 divided by 2, it becomes 5. Now here we have 5. Everyone is pointing to this 17. Now go to mid is 5. So check. Is 17 greater than equal to 16? Yes, this condition is again true. So we can say, yeah, this may be my answer. So update this with 5. But I'm not sure. Loop is still running. I'm not sure. You have to find out smallest index. Maybe you can get a more smaller index to the left hand side. Again, move to the left hand side. So high becomes 5 minus, mid minus 1, that is 4. This becomes 5. Stop. Because condition is not true. Here low is greater than high. And loop will run till low less than equal to high. Because now here we have at 4. First we are having everything here. Now low is here and high is this side. So obviously there is no search space now. Now at last, whatever the position, whatever that element is there, 5, that would be my answer. So at 5, we can insert this 16 here. And that's we can see. Obviously, we can insert 16 here. So this is how using binary search you can find out the insert position. Okay. But if they see there are distinct elements. Okay. So one thing we can say at first only, how to write down this thing. Let me just write down. How to write down. The loop will run till in pseudocode if you want to write down. So while this low is less than equal to high, till then we are going to run the loop. Mid, you have to find out mid is equal to low plus high divided by 2. But generally we don't write this thing because sometimes this can be an overflow case. Low is also very high, a large number. High is also a large number. If you add this, so the range, it would be out of the int range. So some overflow kind of thing. It will give some negative value. That is not allowed. So rather than this, better to write here in this case. I mean, mid is equal to low plus high minus low divided by 2. This is also the same thing. If you take the LCM, then 2 into low plus high minus low, that would be low plus high by 2 ultimately. So better to write down something like this so that you can just, you can say, prevent that overflow condition. Now we have calculated mid. Now check if the array of mid equal to target, we can simply return mid because we know that distinct values are there, no duplicacy is there. So if you want to insert here, suppose I want to insert 15. 15 is also already there. So as soon as you get this 15, return that index. That is exactly the problem statement is saying. So as soon as you at first you find out mid, mid is itself equal to the target. So simply return mid. That's it. Why to go for next? Okay. But now if this is not equal, in that case what happens? Else if my array of mid is greater than target. Now, if it's greater than target, this may be my answer. May be my answer. At first, you can take a element position. That would be n. N means array length of the array. Okay. So now I will change my position. This may be my answer. Position is equal to whatever the mid is, but I'm not sure this is my answer. Array of mid is greater than target, but it may be my answer. Like in this case, 18 can be my answer, but you have to find out smallest index. So now position may be that thing. We just updated the position, that element, but move to the left hand side to find out smallest index. High becomes mid minus 1. Simple. Else you have to do low is equal to mid plus 1. That's it. Simple. At last you simply return whatever the position is. This is how you can find out the insert position of any element with the distinct values. This is specially for distinct values, not duplicate values. Because if there's duplicate values, here also I'm having 15, 15, 15, 15, 15, 15. All these elements are 15. Target is also 15. So at first, binary search, at first mid would be here. This is 15. So you will simply return this index. But no, there are so many 15s here. So this kind of thing will not be allowed in duplicate elements. This, if array mid is equal to target return mid, this condition you can only write when it's given array are of distinct integers. You have to take care of this thing. Okay. If everything is 15 till here, so definitely if new 15 you want to insert, at first you will insert 15 here. Yeah, we can insert 15 here at second. So better to go for the smallest index which is greater than equal to the target. So in that case, this would not be a case. You will simply write if array of mid greater than equal to target, go for this, else go for this. There is no separate equal to type of thing in case of duplicate elements, right? Let me show you the practical now. So let's create a new Java class. Search, insert position we are discussing. Let's go for the same thing. Nums is equal to this and target is 5, whatever is there in the LeetCode. So you have to search insert position. So we just call a method like search insert position, and then you pass the array, whatever the array name, it's nums, not arr, nums, and whatever the target is there, just pass these two things. Okay, let's define this here. Static, it will return the position, so the return type should be int search insert position, and we are passing the array, so here we should have an array, and here we have int target. So you can take the same array, or the name can be different, it can be arr or nums or anything, and target. So better to take here nums, because in LeetCode we are having here nums, so that if you have to submit, you can easily submit. At first, we just have the loop will run till the array length, the length of the array. And what we have to compare here is, if the arr of I, the element, sorry, arr of the element is what, greater than equal to the target given. As soon as you find it, return whatever the index you have at that time. Otherwise, after this for loop, if this is not the case, simply return whatever the length of the array, arr dot length. Simple. So that's the linear search approach. So it is returning some int value. So we can have like int, we can have one thing in result, we can just store this, and at last we can just print whatever the result is. Let's run this. Let's see what is happening. 1 3 5 7, so it should return 0 1 2 2, because 5 is already there. So yeah, it's 2. If here I go for 8, so it will give me 4, the length of the array. Index is 4. Okay, fine. If I write here 0, so obviously 0 you can insert before 1, so at 1 first index, 0th index, so 0 itself. So this is a linear search, but now you have to optimize it. Go for binary search. Let's now comment out this thing, and now we write for binary search. Now apply here binary search. For that, you have first low would be 0. We have one more pointer, that is high would be whatever the length of the array, that is arr dot length, we know -1. Two things we have. Let's take one position is equal to whatever the uh, array dot length, that's, we have position by default, hypothetical value is whatever the length of the array. Now loop will run till low is less than equal to high. Once this condition is not true, just exit. So in this, just find out mid. So mid would be low plus, we write here high minus low. In another like alternative way of writing low plus high is this. Just write down this thing. Now check. If, as we have arrays are of distinct value, so if arr of mid, as soon as you find equal to whatever the target is, you simply don't need to do anything, just return mid. That's it. Don't go further. So it's like the best case. But it's not the case if you have to find out all the cases. So we can say if. Now no need to write down here else if, because if this is true, then simply return means out of this method where you are calling, that it will return. Okay, if this is not true, we go to the next statement, which is after this if. So just write down if. Now check arr of element is at mid, because we can access only three elements from that binary array: first, last, and the mid element, because 3 pointers we have right now: low, high, and mid. So if this mid greater than a target, yes, this may be my answer, but I'm not sure. So this position, now just update the position is equal to mid, but I'm not sure. Smallest index we have to find out, so go to the left half. So to go to the left half, you have to do high is equal to mid minus 1. Simple. Else, if this is not true, then low is equal to mid plus 1. That's it. Because if a target is, or mid is greater than target, then it's okay. This would be case. If mid is less than target, means target is greater than mid. So if it's greater than, then definitely it will, we can get that in the right half the array. right half of the array. So to go to the right half, you have to move low pointer. Low would be mid plus 1. That's it. At last, whatever the position, return that. Simple, right? And if you don't want to take this POS type of element, then there's one more way you can return at last whatever the low pointer is. Okay, but this is the simpler one. That's why you can, if you're a beginner, you can easily get this thing because we are taking a separate position kind of thing. If you get familiar with these problems, after that, rather than taking a separate variable, you can just return sometimes low, sometimes high in some problems. That's allowed. Okay. Okay. Now let's see. Let's try to run this. For 0, it will give you 0 index. Okay, it's running fine. Let's suppose I want to insert 5. 5 is already there, so it should return that index, that is 2. So it should return 2. Okay, fine, we are getting 2. Let's go for target 7. Sorry, not 7, it's 8. So it should run me 4. So yeah, it will give you 4. See, right? Let's try to submit this answer on LeetCode. So we just copy paste our answer. We'll return POS, and here we have this method. So you have to just insert the logic here. That's it. Don't need to do anything or the main or that kind of thing. Simple. Look here, the name is nums. See, array name is nums. So, and I have taken ARR. So I have to change it everywhere. So I guess we are done. So yeah, accepted every test case. Now you can submit it. You can submit it, and that's it. So I guess the questions are not that much tough. You can easily do this. If you want to analyze the complexity, then you can analyze your complexity, and it's login. See, login, and that's exactly they want. In description, you can see login runtime complexity. I hope you got this. So if you want me to solve more such kind of problems or any specific lead code problem, you can just let me know in comment section. So that's it for this lecture, and we have just solved many lead code questions in my course also. If you want to check out, you can go and check out my DSA with Java course. So that's it for this lecture. Now I'll see you in the next lecture. Till then, bye bye. Take care.